All right, guys, so we just finished a few examples of trying to find the slopes of lines that pass through a couple of particular points. Now we're going to start transitioning into this larger category here of trying to write linear equations. But to do that, we've got to talk about the three primary forms of linear equations that are out there. Now, the one without question that geometry students are the most familiar with, and therefore the one you guys like the most, and it's also the most useful of the three we're going to learn, is slope-intercept form. So I'm hoping just hearing that name makes you remember it a little bit. So the general equation for slope-intercept form is y is equal to mx plus b. So again, I'm hoping you guys recall that one already. However, I'm always a little skeptical of just throwing a formula up on the board and expecting that you guys know completely what it means. Three things we need to know about slope-intercept form, everybody. In this form right over here, the letter m, as we've been talking about so far in this section, represents the slope of your line. B, the number that's added at the end after the variable term, b, is going to be the y-intercept of your line. All right? If our line is a function, as long as it's not a vertical line, a line can only cross the y-intercept once at one unique point, and that value is going to be b. So that takes care of the m and the b, but the two things we haven't talked about yet are the y and the x themselves. And what's important to understand is that usually when we write an equation in slope-intercept form, we only put in values for m and b. The y and the x are going to stay there. Okay? But one important thing to be aware of, though, is that you can always kind of test if a point is on a line, because the ordered pair that comes from putting those two numbers together, x, y, can be used to represent any point on the line. Okay, so that's kind of something that we use as a test, and we might come back and talk about that a little bit later. But usually, y equals mx plus b is what we're talking about with slope-intercept form, and we only put in values for m and b. So an example of slope-intercept form might look something like y is equal to 2x plus 3, where your slope would be 2 and your y-intercept would be 3. So that is just kind of an example of what that might look like. Okay, the second one we're going to talk about is one that usually when I ask, it's one that students have maybe heard about before a little bit in Algebra 1, but they're certainly not very comfortable with or very familiar with. But this is one that we're going to start using a lot more in here throughout the course of the year, and that's point-slope form. Point-slope form is really, really useful in certain cases, and we're going to get into that today. The general equation for point-slope form is y minus y sub 1 is equal to m times the quantity of x minus x sub 1. Okay? That is the equation here for point-slope form. Now, what I'm about to show you isn't really necessary here, so you probably don't want to write this down. But if you're ever wondering where this very strange-looking form comes from, well, in certain ways of writing it, again, I wouldn't put this in my notes if I were you, you could put little subscripts of 2 right there on the x and the y. And if we were now going to try to solve this equation for m, we would divide both sides by the binomial quantity of x2 minus x1. And if we do that on both sides, I'm wondering if you guys see it. That binomial quantity cancels with that binomial quantity, and this is what you end up with. If I read it backwards, m, the slope of our line, is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That is the formula for slope, everybody, that we talked about in the previous video. But like I said, knowing where it comes from doesn't really help you out all that much. So let's make our quick little list over here to the side of what everything stands for here. Yet again, lucky for us, the m still represents the slope of that line. And what happens now is that x1 comma y1, kind of like the x and y did in the previous thing we wrote down there for slope-intercept form, the x1, y1 represent the coordinates here of any point on the line. Any point on the line. So there's a big fundamental difference here, everybody, between slope-intercept form and point-slope form. Every single line has only one slope, one unique slope, and one unique y-intercept. So every line out there has one and only one slope-intercept form. We all could do the same problem if there were 20 or 30 of us in the room, and if we were coming up with an answer in slope-intercept form, there's only one right answer that we all should get. But to write an equation in point-slope form, well, every line has only one slope, that's true, but every line passes through an infinite number of points. And since the x1, y1 can represent any point located on a line, and there are an infinite number of those points, there's actually an infinite number of point-slope forms that any line could have. Usually we'll get it down to one or two options, but technically there are more. So an example of a line in point-slope form, let's go with something like this, guys. What if I said something like let's go with y minus 5 is equal to, I'm going to go with a negative 2/3 times the quantity of x minus 1. That's an equation in point-slope form. And to read the relevant information out of that, m, the slope of that line in green, would be negative 2/3. So this would be a line that would be falling from left to right. You'd go down 2 units and 3 to the right. But this line right here starts from the ordered pair 1, 5, both positive values. Because if you go back and look at the formula itself, x sub 1 is the number being subtracted from x. Y sub 1 is the number being subtracted from y. So there's this goofy relationship here where that looks like a negative 1, but it actually passes through an x-coordinate of positive 1. And that negative 5 is actually positive 5 as well. So, as I said, slope-intercept form is the one that students at this level are the most comfortable with. Point-slope form is probably more useful to us in a wider variety of cases, so we're going to get a little bit more practice with that moving forward there. Now the third one I put on here just because I would have felt guilty if I didn't have it on there, guys. This third one is called standard form. And standard form really doesn't serve any great purpose for us. It looks pretty, but that's really about it. The equation for standard form, for some reason we use capital letters here as I've always seen it, is ax plus by is equal to c. So the takeaway from standard form, first of all, it's different from the other two forms that we've talked about in that x and y are both together on the left-hand side of the equation. C, which doesn't have an x or a y there, is a constant value, and that's off on itself by the right. Now there are rules for standard form, everybody. Very quickly, a, b, and c have to all be integers. None of them can be fractions or decimals. A has to be positive. You can't lead this thing off with a negative. And the last one there would be that those three numbers, A, B, and C, have to be relatively prime to one another. If there's a common factor of 2, for example, you have to divide everything out. But I'm not going to make you write those down or memorize those. We're not really going to use standard form for anything in here this year. But that way, if you do see it next year in Algebra 2 or 2 years down the line in pre-calc, you can say, oh yeah, we talked about that for 10 seconds. All right, so with those in mind, let's start talking about graphing linear functions, everybody, or graphing linear equations. And the first one we have here is y is equal to negative 2x plus 3. Now, the most important thing to understand, I think even more important than how we do this, is what in the world it is that we are trying to accomplish here. Now, in basic Algebra 1, if you saw a one-variable equation, like like 5x plus 1 is equal to 21. This is an equation that in Algebra 1, they would ask you to solve. You'd subtract the 1, you divide it by 5, and you would get x is equal to 4. In a simple one-variable equation, there is usually only one solution, at least for most of what you saw in Algebra 1. 4 is the only value that you can put in here for x and make a true statement, because it's true that 5 times 4 plus 1 does equal 21. So that's just a quick, kind of synopsis here of what we're doing when we solve linear equations. But in a two-variable equation like this, everybody, there's not one simple answer, like, for example, x equals 4. The solution to a two-variable equation has to have a value of both x and y. And what I'm hoping you guys remember from last year is that when you put an x and a y solution together, we do it as an ordered pair. Now you don't need to write this down, but just humor me for just a second. And what you're going to find is that there are lots of solutions to this. For example, when x is 2, negative 2 times 2 would be negative 4 plus 3 makes negative 1. The ordered pair negative 2, 1 is a solution here because when you put the negative 1 in for y and the 2 in for x, we should get a true statement. Let's check that. Negative 1 should be equal to negative 2 times an x value of 2 plus 3. Well, that makes negative 4, and negative 4 plus 3 is negative 1. Check. That one works. So 2, negative 1 is one solution to this equation, but it's certainly not the only one. For example, if I put in a negative 4 for x, 11 would work for y, because 11 is equal to negative 2 times negative 4 plus 3. Yeah, that's right. So there's a second solution. And guess what? There's a third one. If I put in 100 for my x value, negative 200 plus 3 is negative 197. That one works as well. And I could continue to do this all day long. So there isn't just one solution to a two-variable equation. In fact, there are infinitely many. So instead of asking you guys just to list all of the solutions like we did back in Algebra 1 with simple equations, we can't do that now because it's too complicated. But what we can do instead is draw a visual pattern of what all of the solutions to that equation look like. And that's what you're doing when you graph a line. Okay, enough of that theory. Let's start talking about how to actually do this. The first thing we better do is recognize what form this equation is in. Y is equal to a coefficient times x and then plus a number at the end. This, everybody, is slope-intercept form. Y equals mx plus b. And the first thing we need to figure out then, if it's slope-intercept form, what's our slope and what's our y-intercept? Well, the slope is always the coefficient of x, the number in front being multiplied. Our slope here is negative 2. And while that's true, we're going to like to think of slope as a fraction, so we can do rise over run. So anytime your slope is an integer, let's just go ahead and put a 1 underneath that. B, the y-intercept, is the number that gets either added or subtracted, usually at the end, although not always, on that right-hand side. So our y-intercept is a positive 3. And armed with these two pieces of information, you guys, we now know everything we need to know about this line, because there's only one line that has a y-intercept of 3 and a slope of negative 2. We deal with the y-intercept first, everybody. The y-intercept is the one point where this line crosses the y-axis. So we start thinking about this at 0, but a y-intercept of positive 3 means we go up. 1, 2, 3, and that means that our line is going to pass through that point right there at a coordinate of positive 3, but on the y-axis. Ladies and gentlemen, I'll see a lot of people at this level put their first point right here. What I've done right there is I've shown an x-intercept of 3. That's where this line or this point is crossing the x-axis. But we want to do a y-intercept, so it needs to be up on this vertical axis right here, and there we go. And now that we know where our y-intercept is, we treat that as our starting point. And now it's time to think about the slope. So the y-intercept tells you where to begin from. The slope is now a set of directions that tells you where to go. And our slope, our rise over run, is negative 2 over 1. That means that from this starting point, we are going to rise negative 2, which means we go down 2 units, and run positive 1, which means 1 to the right. So down 2 and right 1 gets us to this point right here. Now, technically, everybody, we're done. We've come up with 2 distinct points on this line, and one of the fundamental ideas of geometry we've been talking about all year is that there is only one unique line that is determined by 2 points. However, it's always a good idea for us to go further and use our slope multiple times. So I'm going to continue to do the same thing. My rise of -2 and my run of 1 means I go down 2, right 1, and make another point. Down 2, right 1, make another point. Down 2, right 1, make another point. And here's a word you probably didn't know last year in Algebra 1, but hopefully now you do. Those 5 points are all collinear. They're all on the same line. The other thing you could have done, if you were so inclined, is remembered that a fraction that has a negative value, well, that negative could be put on the bottom just as well as it could be on the top. That's really the same as +2 over -1. And now if I read that slope, my rise looks like it's +2, which means I would go up 2 units. But my run is now negative, which is going to move us to the left. So if I went back to this same starting point right over here and now thought about a slope of +2 over -1, that would tell me to go up 2 and left 1. Well, sure enough, that now gives me a 6th point that's collinear with the other 5. And now that you've drawn those 6 points, now it's time to go ahead and just connect the dots and make the one and only line, this is hard to do with my shadow in the way, the one and only line that passes through all 6 of those points. And when the directions say graph each line, we are now done. However, I'd love to go just a little step further to show you guys what we just accomplished. For example, every one of these points that's on that line, like maybe this one right over here, which seems to have the coordinate of 4 and then -5. Every one of those points is on that line for a reason, everybody, because every one of those points satisfies this original equation. Let's check that and see if we're right. Y equals -2x plus 3. Well, at this point, our y coordinate is -5. So that's y. That equals -2 is our slope times our x coordinate of 4, and then a plus 3 at the end of that. Let's see if that's a true statement. -2 times 4 is -8. -8 plus 3, yep, equals -5. Check. Now that wasn't just a lucky coincidence, everybody. For example, this point right over here looks like it is -1 and then 5 for its y coordinate. So let's try putting those numbers back into this equation too. Y here is +5. That equals a slope of -2 times an x coordinate of -1 plus our y-intercept of 3. Let's test that. -2 times -1 is 2. And 2 plus 3 gets us 5. Check. That one works as well. So once again, everybody, there are an infinite number of solutions to this equation here. I can't ask you to list them all, but what I can ask you to do then is draw me a picture. All right, and that picture then shows the visual pattern of where all of the solutions to this equation are located. So let's put together an algebraic and a geometric idea. Algebraic idea, there are how many solutions to this 2-variable equation? Infinitely many. And the geometric idea, there are how many points located on a line, everybody? And the answer to that is infinitely many as well. Every point on the line is a solution to the equation, and then flip that around, every solution to the equation can be found as a point on the line, an infinite number in each case. Okay, hopefully that rings a little bell from last year. Let's move on to a second case like this. And there are 2 different ways of graphing an equation here written in this manner, and I kind of want to show you my preferred way, but I also need to acknowledge that most of you are going to ignore me and do it the way that you want to do it. So let's talk about this instead. The first thing I would ask you guys to do is to think about what form this equation is in. We've got y plus 2 equals 3/4 times x minus 5. If you go back and check your notes, everybody, this is point slope form to a T. All right, and 2 things we can read about a line in point slope form. The slope of your line is the coefficient in front of the binomial on the right containing an x. So your slope here is +3/4. The other thing that we can learn from point-slope form is a point that the line passes through. Now, it's not a special point like the y-intercept was. It's just a random point. And that ordered pair comes, and this is a little tricky now, by taking the opposite of this number here and the opposite of this number here. So the opposite of that -5 right there is +5, and the opposite of a +2 is a -2. So if we've done this right, this is kind of the information we've pulled out of this equation. We believe that this line here has a slope of 3/4 and passes through the point 5, -2. Now, in the last example, when we graphed a line that was in slope-intercept form, we dealt with the y-intercept first. That got us our starting point. Then we worried about the slope to use that as a set of directions to figure out where to go. The same basic concept applies here. The only difference is that this point right here isn't anything special like your y-intercept. It's a random point, but that is good enough, everybody, to be our starting point. So we're going to begin this line at the random point of 5, 1, 2, 3, 4, 5, -2. That's going to get us to right here. In fact, I'm going to go ahead and label that as 5, -2. And I want to make sure, before I go any further, because I know you guys aren't real comfortable with point-slope form, let's make sure that that point is actually on this line. How do we do that? We plug and chug and we make sure this works. In for the y value right here, we put this y value, which is -2. Then what comes next? +2 is equal to our slope, which is 3/4, and then in parentheses, this x right here gets replaced with this x coordinate, which is 5, and we follow that up with -5. Now, is this right? Yeah, I'm pretty sure it is. On the left side, -2 + 2 is 0. That equals 3/4 times 5 - 5, which is 0 as well. So we end up with 0 = 0, and that one works out. So now that we've established that our starting point is correct, now it's time to use the slope as our set of directions for where to go next. And with a slope of 3/4, from our starting point, we are going to rise 3 units, which means go up 3, and run +4, which means go right 4. So from this spot here, everybody, we're going to go up 1, 2, 3 units, and then to the right, 1, 2, 3, 4 units, and we put a big dot right there. I'd love to do this again, but I'm out of room. I can't go any further to the right. So let's reverse it. This is a weird thing to think about, but +3/4 is really the same thing as -3 divided by -4. A negative divided by a negative is still positive. So from my initial starting point at 5, -2, I could also go down 3, 1, 2, 3, and then left 4, 1, 2, 3, 4, and that would get us to this point right here. And sure enough, it looks like, since we've done this well, that those 3 points are collinear, and that is what this equation would look like. Okay? All right. The other way to do this problem would have involved kind of being wimpy about it and trying to put this thing into slope-intercept form by distributing the 3/4 and then subtracting 2 from both sides to isolate the y. It would have worked, but with this one, you would have ended up with some really ugly fractional values there, and I think it's really better to do it this way. And the last one I'm going to do with you right now before we wrap up this video is graphing one out of standard form. Now this one, we're going to do exactly the way I just mentioned the last one. I don't want to bother teaching you guys and having you remember that, oh boy, that the slope to an equation in standard form is -a/b, or that the y-intercept is c/b. Nobody cares, and nobody's going to remember that. So if we have an equation that's in a form we don't recognize, let's put it in a form that we do recognize. And slope-intercept form is everybody's favorite. We're going to follow the rules of algebra here. We're going to subtract a 2x from both sides. That is going to get us 5y equals, and technically my right side is 15 minus 2x, but most people prefer that with the x term coming first and the constant at the end. And the last thing we have to do now is divide out that 5. And if we're going to do this, everybody, we have to divide every term in the equation by 5, so don't forget that 15 at the end there. These 5's cancel, and we're going to get y equals. Now nothing good happens here, so it's negative 2/5. Let me take that back. We usually like the negative on the top, so I'll do it that way. Negative 2/5. The x I just put right there, and then a plus 3. So now that equation is in slope-intercept form, where your slope is equal to negative 2/5, and your y-intercept is equal to a positive 3. Feel like we've done this already. So with a y-intercept of 3, we start at that point right there. With a slope of negative 2/5, we're going to go 2 units down and 5 units right. And it looks like that. Let me do it again. 2 units down, 5 units right gets us here. Hey, let's reverse it. 2 units up, 5 units left gets us right here. So that's 4 points right there, and they certainly all look collinear to one another. So that is the graph of the equation 2x plus 5y is equal to 15. Okay, everybody, that's a good spot to stop this second video. We'll pick it up with part 3 pretty soon here. Good luck.